Welcome back. We continue our study of chapter 4 and now we move to section 4.2 about the weak topology on a norm space. So we'll apply the general construction of the previous section to the case of a norm space and some special collection of maps. So in order not to make lengthy videos, I will split this section to 3 videos. In this video, I'm going to give the definition and some basic properties. And we'll continue our study in the next video. Okay, so given a norm space E and an element F in the dual of E, we set phi sub F to be F. And so as F varies in E star, we get a collection of maps from E into R, because F is just a linear map from E into R. So in the notation of the previous section, we take X to be E, the index set I to be E star, in which F varies, and the target spaces Yi are all the same. They are equal to R. And once again, R is equipped with the absolute value, and so is the usual topology. Okay, so the norm on R is the absolute value, and the index I is F. Okay, so the smallest topology making continuous this collection of maps is called the weak topology on E. And it's denoted by sigma of E star. So now we have two topologies on E. The norm topology, or the usual topology that you are familiar with from second year. What is it? When we have a norm on a space, this norm defines a distance, and a distance defines the notion of a ball, and with the help of balls, we can define the notion of open sets. Okay, so a set is open relative to this norm topology if whenever it contains a point, it contains a ball around that point. So this is the norm topology that we may call also strong topology. In contrast with this new one that you are just defined, which is called the weak topology. Okay, so the first question is, how do they relate? Is there any relation between the two? Yes. So the answer is that the weak topology is smaller or weaker, if you like, than the norm or strong topology. Why this is so? It's very easy. Each F or each phi F is continuous with respect to the norm topology, but the weak topology is the smallest topology making continuous these maps. Okay, so it's contained in any topology making continuous these maps. So in particular, it's contained in the norm topology. Okay, so this means that the weak topology conserves the continuity of the elements of E star. So the elements, the linear maps, which were already continuous, remain continuous with respect to this new topology. So this is a big achievement, because we had two birds in one stone. From the one hand, we defined a smaller topology. So we have now more compact sets, more connected sets, more convergent sequences, but at the same time, we didn't lose the continuity of at least the linear maps from E to R. Okay. However, we may lose the continuity of non-linear maps from E to R. Okay. This is explored in the exercises. So, and a very useful remark, which also may seem a little bit confusing in the beginning, if F is a linear map from E to R, then F is continuous for the norm topology if and only if it is continuous for the weak topology. Okay, we have an equivalence here actually. So think of this a little bit. Take a paper and a pen and write down the simple proof. It's very simple. Okay, so everything follows from the definition here. Okay, so when I take So I have two topologies, but when f is linear, saying that f is continuous for the norm topology is the same thing as saying that it's continuous for the weak topology. And we shall use this fact very often. Okay, now, yeah, I said this, the norm topology is called the strong topology. Second remark about terminology. If you have a topological property or adjective like compact, continuous, and so open, and so on, we'll say that an object is weakly P or satisfies the property P weakly if it has this property P with respect to the weak topology. Okay, so for example, a map from E to R is said to be weakly continuous if it's continuous with respect to the weak topology, which means that the inverse image of an open subset of R belongs to the weak topology. Okay. A subset K of E is said to be weakly compact if it's compact in the weak topology. Same thing for open, closed, and same thing for weak conversion. So when I said that a space is weakly closed, it means that its complement belongs to the weak topology. Okay. A sequence is weakly convergent if it's convergent in the weak topology. So it means that every neighborhood of the limit contains the sequence starting from the certain rank. Okay, now what are the basic properties of this topology? First result is that this topology is Hausdorff, and this is something desirable because the Hausdorff condition rules out some unfamiliar and weird cases like sequences converging to more than one point. Okay. In a Hausdorff space, a sequence converges to at most one point. And many interesting theorems do not hold in non-Hausdorff spaces. Why this is so? It's very easy. Take two distinct points, x1 and x2. By the Hahn-Banach theorem, we can separate them by a closed hyperplane, which means that, in particular, there exists an element in the dual. So it's continuous for the norm and for the weak topology, and the number alpha such that f of x1 is less than alpha less than f of x2. And now I just take O1 to be the set of x whose image under f is strictly less than alpha, which is just the inverse image under f of the open interval minus infinity alpha, and O2 to be the set of elements whose image under f is strictly bigger than alpha, which is the inverse image of the open interval alpha plus infinity. So now, since f of x1 is less than alpha, it means that x1 is in O1, and similarly x2 is in O2. Now O1 is open in the weak topology. Why? Because it's the inverse image under a weakly continuous map of an open interval. Same thing for O2. So O1 and O2 belong to the weak topology. They are weakly open sets, and they are, of course, disjoint. So we separated x1 and x2 by two disjoint weakly open sets. So this is easy. Next property establishes something very useful in practice, gives us a useful form, a practical form for weak neighborhoods of points. So if x0 is a point in E and epsilon is a positive number, and we have finitely many elements in the dual of E, we consider the set that depends on x0, the f1 through fk, and epsilon. It's what? The set of x such that the absolute value of fi of x minus x0 is less than epsilon. And I can write this in several ways. So, because now note that fi of x is a real number. So this is why I took the absolute value. So it means that minus epsilon, so fi of x minus x0 is between minus epsilon and epsilon. Or if you like, fi of x is between fi of x0 minus epsilon and fi of x0 plus epsilon. If you write this is a double inequality actually. Okay, so first conclusion is that this is a neighborhood of x0 in the weak topology. Okay, so, and actually it's an open set in the weak topology. And second result is that when I vary epsilon and the elements in the dual, but they are still finite, we obtain a basis of neighborhoods of x0, and I will explain what I mean by that in a moment. Okay, so first, the result is easy because, as you observed, x is in V if fi of x for every I between 1 and k is between fi of x0 minus epsilon and fi of x0 plus epsilon. So x is in the inverse image under fi of this open interval. And since this is true for every I, then x belongs to the intersection. So it's easy to see that V is a finite intersection of inverse images of open intervals. And once again, since fi is weakly continuous, it's inverse image under fi of an open set is an open set. So, and then I have a finite intersection of open sets, so it's open. So V is an open set, and of course it contains x0 because when I put x0 here, I get fi of 0, which is 0, so of course it's less than epsilon. Now what happens when I let epsilon and the fi vary? I get what I call a basis of neighborhoods. What do I mean by that? It means that every neighborhood of x0 in the weak topology contains a set of this form, okay, for certain epsilon and k and f1 through fk. Okay. Now the k is could be anything, could be 1 actually, could be 2, could be 10. So we could have just one f and one epsilon. So if U is an open neighborhood of x0, by definition of the weak topology, we have a formula, as you know. So an element of the weak topology is an arbitrary union of a finite intersection, or equivalently, every x0 if x0 is in U, then there exists a basis element, which is a finite intersection of inverse images of open sets. So this is what we call a basis element. So I can find a basis element containing x0 and contained in U. Now what does it mean that x0 is in the intersection? It means that x0 is in each one of these sets. So x0 is in fi minus 1 of oi for every I. And this means that fi of x0 is an oi by definition of the inverse image. So now we are working in R here. x0 is a vector, fi is a linear map, but the fi of x0 is a number. So what does it mean that this number is an open subset of R? It means, by definition, there is a ball or an interval in R of center fi of x0 contained in OI. So for each I can find an interval, an open interval of radius epsilon I contained in OI. And now I just take epsilon to be the smaller one between these epsilons from I from 1 to k. Then I get fi of x0 minus epsilon, fi of x0 plus epsilon is contained in OI. And this precisely means that for this choice of epsilon and fi, I get this neighborhood, and it contains x0, of course. And this neighborhood is contained in the intersection of fi minus 1 of oi. Because if an element is here, it means that, so call this element y or x, right? So it means that fi of x is in this interval. So fi of x is in oi, and this means that x is in fi minus 1 of oi, and this is true for every I, so x is in the intersection, and the intersection is by construction in U, so we have this. So every weak neighborhood of x0 contains a set of this form. This should put here x0 actually. Okay, so whenever we will deal with weakly open neighborhoods of points, we can assume that they have this special form. So it's very convenient. Okay. Okay, now we move to the next result about convergence in the weak topology or weak convergence. So if a sequence in E converges to X in the weak topology, you will write X in semi-arrow X. And the norm convergence or the strong convergence will be denoted by the usual arrow. Okay, so we have two kinds of convergence now in a norm space, strong convergence and weak convergence. And I want you to pause the video and think which one imply the other. Strong convergence implies weak convergence, and because the strong topology is bigger. Okay, so, and we observed that earlier. So a smaller topology contains more convergent sequence, if you like, if you want to put it in this way. Okay. And there is another way to see that after I establish this proposition. So if Xn is a sequence in a norm space E, then Xn converges weakly to X if and only if the image of Xn under any element in the dual converges to f of X in R. Okay, and this is a very useful criterion because it's easier to deal with real sequences than with sequences in an arbitrary norm space. Okay, so once again, Xn and X are in E. F lives in the dual of E, but f of X and f of Xn are real numbers. Second property is that a weakly convergent sequence is bounded. We know that for strongly convergent sequences, but the result is true. So a weakly convergent sequence is bounded, and the norm of the limit is less than the lim_inf of the norm of Xn. And here I use lim_inf because it's not necessarily true that the norm of Xn is convergent. Okay, it's possible that the norm of Xn converges to X, but the norm of Xn does not converge. So this is why I took the lim_inf. And last property, if Xn converges weakly to X and if n converges to f in E star, so strongly in E star, then Fn of Xn converges to f of X in R. Okay, so the first property is, there are two ways to see it. Actually, no, one way. So this is just a consequence of proposition 4.1, which states that with respect to the topology generated by a collection of maps, a sequence is convergent if and only if it's the images of the sequence under all maps converges. And this is what we have here. So the f is just the phi sub f. Okay, so this is the first point. Second point, since if Xn converges weakly to X, then f of Xn converges to f of X, and every convergent sequence of real numbers is bounded. But, and this is where this is very something that, so by a corollary of the uniform bound principle, Xn is bounded. Okay, this is very important. So it's easy to prove that something is bounded to look at its images under all linear bounded maps. Okay, why the lim_inf? Because we write the fundamental operator inequality, f of Xn, in absolute value, because the absolute value is the norm on R, is less than the operator norm of f, or the norm in E star, times the norm of Xn. And I take lim_inf on both sides. But lim_inf of f of Xn is just the limit because the limit exists. Okay, and it's just f of X, so an absolute value. And this is a constant, so I can put it outside the lim_inf, and I get norm of f times lim_inf of Xn. And now I use a corollary of the Hahn-Banach theorem, which tells me that, so in particular, this is less than the lim_inf of Xn for all f in the closed unit ball of E star. So the sup of this quantity when f is in the closed unit ball of E star is just the norm of X, okay, by the corollary of the Hahn-Banach theorem, and therefore I get that. Okay, the last property follows from, this is a standard argument that you must master. So we add and subtract similar terms. So we write the difference. We add and subtract f of xn, and we take the absolute values by the triangle inequality. So we have two terms. The first term by the fundamental operator norm inequality is less than the norm of fn minus f times the norm of xn. This is the first term. And the second term tends to 0 because xn converges weakly to x. Now, fn converges to f in the operator norm, so this tends to 0, and this is bounded. This is important. So this tends to 0, this tends to 0, and this is bounded. So the product tends to 0. Okay, so this concludes the proof of this proposition and this video. In the next video, I'm going to dig deeper into some properties of the weak topology. So thank you for your attention and see you next time.